In this problem, we have a system which is made up of a block A and a cart B. We know the mass of A, it's M. We know the mass of, I guess we don't actually know the mass of the cart, but if we need to have it, we'll just call it big M. And what we know is that the block and the cart are connected by two springs. On the left side, it's 3K. On the right side, it's K. And then between A and ground is a third spring, which has a stiffness of 2K. What we also know is that the cart is given a prescribed motion of XB. So XB is, if we look back up here, it's prescribed, and it's given by some magnitude B times cosine omega t. And what we want to do is end up with a differential equation which describes the motion there of block A. So again, the input, if you will, is the motion of the cart, and eventually what we want to do is talk about the dynamical motion there for A. Okay, so let's do our FBDs. In fact, let's just focus here on A. On A, the displacement of A is given by X. So if we look at the three spring forces, the one here, the one here, and the one over on the right, on the left hand side, the first one there on the top right, that compression is going to be X, stiffness is 2K, and since X is being positive to the right, that would correspond to a compressed spring. Spring on the lower right, the one with stiffness K, it is going to be the difference between the motion of A and the cart. It has a stiffness of K, so it's going to be K times the difference. And it doesn't really make any difference which way we write this. I'm going to write it as X minus XB. Okay. Again, the force isn't just related to X. It's actually the difference between the motion of the two endpoints of the spring. One endpoint on A is X, and on a cart it's B. So the difference. But now let's figure out what sign, what direction we have for that force. When X is larger than XB, X larger than XB, it means that the block is moved further to the right than the cart, so that spring is compressed, so that force is acting to the left. Same way with the spring there on the left. Its stiffness, 3K, but its displacement is the difference between X and XB. Let me just write it as X minus XB. In this case, though, when X is larger than XB, A is moved more to the right than the cart, so that's going to stretch that spring. So that force stretched, but it still points to the left. Okay, so that's really what we need. Let's now use that FBD in order to come up with our equation of motion. So we'll use the Newton-Euler equations for block A. And if we sum forces in X is positive to the right, we have a minus 3K X minus XB. We have a minus K X minus XB. Minus 2kx. They're all pointing to the left, so that's a minus sign on there. Then that's equal to the mass times x double dot. So if we rearrange our terms, bring all the x's on the left side, it's got mx double dot. For the x's, we got, 3, 4, 6. So it's going to be 6kx. And all that's left on the right-hand side is going to be a 3kxb plus a kxb, so that's a 4kxb. And we said that xb was equal to this amplitude b times cosine omega t. So there it is. This is our equation of motion. In order to find the natural frequency. We'll divide by whatever is the coefficient of the leading term, that is coefficient of x double dot. So we get x double dot plus 6k over m x is equal to 4k over m b cosine omega t. Now what we've learned from class is that whatever coefficient appears in front of x once you put it in its standard form, that's equal to omega n squared. So the natural frequency omega n is equal to 6k divided by m with the square root. So we have enough that we can get a numerical value for omega n. The last part asks for us to come up with the particular solution. That is just the part due to the forcing. With the excitation being a cosine, what we can do is say the particular solution xp is going to be equal to, let's say, a cosine omega t plus b sine omega t. So if we substitute into our equation of motion, what we have is minus omega squared a cosine omega t minus omega squared b sine omega t plus omega n squared times a cosine plus omega n squared b sine omega t. On the right hand side, that's going to be 4k over mb cosine. So what we're doing is taking a known result, substituting in, and our goal is to find a and b. If the left hand side is equal to the right hand side, all coefficients in front of cosine must balance out. So we have minus omega squared plus omega n squared times a, that's what is appearing in front of cosine, must be equal to 4k over m. So therefore we have a value here for a, that's 4k divided by m divided by omega n squared minus omega squared. We have numbers to put into there. We've got a. The coefficients in front of sine. On the left hand side we have minus omega squared plus omega n squared b. Right hand side there is no sine. So from this we see that for all values of omega we're going to have b equal to a 0. The result, once we have the numerical value for a, you can say then the xp is that numerical value for a times cosine omega t. Okay, so what did we do? We really focused in on the FBD for block A. The key in this problem, I think, is getting the spring forces right. Spring forces depend on the relative motion between the two ends of the spring. So for the spring on the left, the relative motion between A and the base, that's x minus xb. That times 3k is that force. Right hand side on the bottom, the spring again. The compression stretch is given by x minus xb. It's times k. But the spring on the top right is connected to ground, so basically the ground is fixed, so it just ends up being 2kx. We sum forces in x, we get our equation of motion. From that we identify our natural frequency by putting it in standard form. We divide by the coefficient in front of x double dot. And then lastly, the particular solution. Since the right-hand side, the forcing, is cosine, we know the particular solution is some combination of cosine and sine. We just don't know what those coefficients are. But by substituting in there, balancing our coefficients, we find out what A and B are. B ends up being a 0, and therefore we get XP.